The subject today is an introduction to units, measuring, scaling, sketching, and board drafting. This is brought to you by the CAD Academy. I am Stephanie Kwame, and I've been an adjunct faculty member for 24 years teaching technology education at a community college level, and it's my pleasure to be your host today. Did you ever wonder how the distance from the Earth to the Moon was measured? Well, it was measured over 2,000 years ago by the Greeks. I'm sure because they did not have the distraction of televisions and electronic devices that they looked at the heavens more than we do now and pondered the mysteries of the heavens. They figured about 247,000 miles. And according to Universe Today, the distance to the moon is 239,000 miles. So imagine that 2,000 years ago, they were very smart and came very close to the actual distance. And what they did is they started with a known reference point, and that was the circumference of the Earth. They had already figured out, if you know the circumference, you know something is round, and they already had figured out also that the Earth was round. This was called the Age of Enlightenment. The Greek and Roman Empire built beautiful buildings, and there's mysteries about the buildings to this day, and great philosophers like Plato would meet in forums and discuss ideas and concepts and the mysteries of the world. They also left a lasting legacy of architecture, and the architecture is so admired that you can see the influence it has today in our architecture. So if you take a look at our capital in Washington, D.C., you can see that that has a Greek and Roman influence. And like a lot of societies, it fell. And they fell, both the Greek and the Roman society did. And after the fall of the Roman Empire, we actually went backwards, and they saw it's known as the Dark Ages. It's strange because we think that society always gets smarter and better and learns more, and the fact of the matter was we actually had a time when we went backwards, and not only did not learn, we lost what we knew, and many people thought that the Earth was flat, and they thought that if you went far enough to the edge you'd fall off. So in 1492, Christopher Columbus set sail on the ocean to find new land, to find spice routes, and also to kind of prove that that the world was round. Like the Greek and Romans, great thinkers are always thinking of ways to make our world a better place, and that's what engineering is all about. And great thinkers used to think of looking between France and the United Kingdom. They tried to figure out a way they could get across that channel. And the channel is about 70 miles long. So some of the early ideas were, let's go ahead and build this tunnel and build a bridge, and we'll take our horses and ride them off to that little platform in the middle, and then we could either change off horses or let the horses rest and then ride the rest of the way. So this has been thought of for years and years and years, you can tell that. And so what happened is they got serious about it, and in the late 1980s, and decided to build something they called the channel. And there was a lot of civil engineering and geological surveying, but they wanted this to go underneath the channel, so it kind of followed a little line, like a little direction like that. So it was underneath the water and underneath some of the top soil, the top dirt area. And the channel was to have be three tunnels. So they had one going one direction, one going the other direction, and one is a service tunnel. And now they don't do that anymore because of fires that they've had in the channel. They now have an extra tunnel that they can use in case of emergencies. This had, they developed high-speed trains to go into the channel, and what happened is England came from one side and France came from the other side, and they dug, because you can get it done twice as fast, with the hopes that their surveying and engineering was right and they would meet together in the middle. And again, that's a long distance to go. And on August 30th, 1990, they actually broke through with a 2-inch hole, and thank goodness they met in the middle. It takes 2 hours and 15 minutes now to go across there, and before that there was no direct way to get there. And it's a big time saver. And the trains, called the Channel Tunnel Rail Link, go at 186 miles per hour. And it was actually named one of the 7 wonders of the modern world. Now, we've gone from, or tried to look at the distance between the Earth and the Moon. And then we've looked at a big distance of 70 miles between 2 continents. And now, let's talk about the smallest units that you could see. And of course, the smallest would be, particles of matter, atom, and below. But as far as electronics, manufacturing, or architecture, or engineering, the smallest I've ever seen was one day I was at Medtronics, and they do medical devices, diabetic implant devices, and pacemakers. I was supporting the area that supported the machinery. So it was really a mechanical operation. And one of the gentlemen I was working with said, "Come look at this." And I looked at something so small to my eye without being aided. It just looked like a little rectangle. And these are examples of integrated circuits at the right. And the top one is early, and then the next one is a layered circuit. But I looked inside of that microscope, and a whole world opened up to me. There were chips, and even smaller yet would be the leads that came off the chips to connect it. I couldn't even fathom. They told me how small those were. But can you imagine doing the drawings for that small of a distance? In the United States, we use imperial units. And some people say, why in the world are we on imperial units? And the reason being is the people that settled the United States were from England. And this is actually the Weight and Measures Office from about that time. And so the imperial units are based on feet, or units of 12. If you look at the map below there, in red are the nations that still use imperial units. And so even England doesn't use imperial units anymore. Everybody else has gone to metric. And of course, metric is based on units of 10. And where it gets really interesting is if you have a building that's done in architecture, or an architectural building in the US, and it's based on 10 units, or 12 in every unit, and you insert that into a civil engineering drawing that has 10 units, then you have to do a conversion factor. And there's where it gets a little bit interesting. Pieces of paper, or standard paper sizes in engineering and architecture, were determined so that you could put a scaled object onto them. And in mechanical or electronic engineering, sometimes it will be much smaller than an A-size sheet, which is 8.5 by 11. So that would have a scale that would go like 2 to 1, 10 to 1, 1,000 to 1, and or blown up. And then there are many things that you could actually do 1 to 1. Matter of fact, people do patterns off of computer-aided design, or they do even flat pattern layout for HVAC boards, so they can do things 1 to 1. But anyway, the standard paper sizes were done so that we could do a drawing, either to to manufacture or construct something. And notice different scaling factors there. Like scientific, with that E is exponential. With that type of units, I could actually put in the distance from the Earth to the Moon, or even or beyond. And there's decimal units, engineering, architectural, and fractional. So there's a lot of different formats that you could use. In architectural, we usually have, for residential design, 1/4 inch equals a foot. And architects are so used to, they were so used to scaling down, and they were not used to the fact that in CAD, we have a virtual world that we deal with, and everything is one-to-one. So if a wall is 120 feet long, it is 120 feet long in our virtual world. And the program does the calculating when we go to make construction drawings, for instance, and we'll say that this residential drawing, 1/4 of an inch equals a foot, would fit on a standard D-size sheet, and then plot it out to that D-size sheet. There's also conventions for text heights and all kinds of things, and we will be delving deeper into that in the coming lessons. But basically, just understand that there are standard sheet sizes, and there are scaling standards that exist, and it all has to do with putting things on a sheet of paper, and a lot of rules and regulations. For instance, I ran into tolerance dimensioning when I was only 19 years old. I worked in a parachute manufacturing plant that did cargo parachutes for the Vietnam War. They were 150 feet in diameter. They had 20 panels, and each panel was 5 foot wide, and they could only be out 1/4 of an inch. But every panel couldn't be out 1/4 of an inch, because the total varied tolerance could only be plus or minus 2 feet, or it could be 102 or 98 feet. The accountant died soon after I went to work there, and I ended up doing all the duties. So I ended up doing notification of release of shipment, and worked with the government inspector, and I did these things called DD-250s. I looked it up, and lo and behold, that's the form, and they still use it today. It's like a nightmare form to me, because I had to type it perfectly. We didn't have computers back then. But this government inspector would make us tear out a seam if it was 1/8 of an inch off of out of specification. And I tried to explain to him I thought that would weaken it, or weaken the object. It'd be better for him to keep it, to not have to do that. But no, that's what his job was, and he made sure we towed the line. There's also, below is an example of American Society of Mechanical Engineering geometric dimensioning and tolerancing, and that's a big word, but there's they basically have standards, and geometric dimensioning and tolerancing sometimes has to do with machining or manufacturing of parts. So if I looked at those dimensions, I could see that I would have to go over 10 units and go down 5, and there I would have that center point, and then I could drill a hole there. And the annotation, each one of those little letters and numbers has a specific meaning in geometric dimensioning and tolerancing. In our first lesson on SolidWorks, we talked about how engineers start with a sketch. I'm working with an architect right now who's doing a remodel job, and he breaks off all the time and sketches on anything he can find that's by him to explain to me what he's looking for. We were looking for a sliding door, and he couldn't find a pocket door exactly because it had to be in the middle, and he's sketching away. So sketching is something that architects and engineers use all the time. Why do they continue and still use sketching? And you can do it on the computer as well, but I think the art of hand sketching is still important. But it is a very powerful form of visual communication. And even though, the architect can talk to me, I don't really understand what he's saying until he draws it for me. So a quick sketch is a great way to communicate an idea. So sketching, you use sketching to communicate an idea, to work through some thinking on your own, or else confirm what somebody's telling you. I could have drawn, oh, you mean this is what you meant. Sketches are done normally with like a number 2 pencil on some specific paper, but you can sketch anywhere. That's the wonder of it. And over on the right are examples of sketches done on napkins. A lot of great concepts have come out of restaurants, meetings in restaurants. Board drafting is still around, and it's still important to learn, especially for understanding where putting a plan or a drawing comes from. there's nothing like scaling something or using a scaled ruler and producing it's really like a beautiful work of art. The architect I'm working with has drawings from the original house, and they were done on the board, and they really are a work of art. And sometimes, who knows, the CAD machine might be broken down, or you might need to be doing some little simple thing by hand, and so it doesn't hurt to learn how to do a little board drafting. Your instructor can show you what a T-square is, a triangle, a French curve, and a protractor, and perhaps you will be doing some board drafting. With the evolution of CAD and 3D parametric programs, the design became more important than the sheet of paper. Up until that point, I think that sheet of paper was everything to everybody. And now we make 3D objects, we can turn and look at it, and the sheet of paper is done almost automatically. And the products that we work with are both parametric 3D modelers. SolidWorks is definitely one, and our BIM modeler for architecture is ArchiCAD, and they started the building information model revolution. So both of those products are wonderful products to learn, but they do some things automatically, so it's kind of good to go back and learn where the roots came from. So we'll be moving along in other lessons and talking about the glass box theory. I bet you can't wait. But as a review from today, we talked about measure a little bit, scaling, distance, sketching, and board drafting. So hopefully you definitely understand that engineers and architects work with various lengths, measurements, distances, and sizes, and they can go from the universe to something we can't see. And scaling is necessary. You need to scale something if it's any larger or smaller than a standard sheet size. So if you can't do it 1-to-1, then you need to come up with a scale. And there's standard scales as well that we talked about. In the United States, we're pretty different. We work with imperial units, and almost everybody else works with metric. Great ideas can start with a sketch on a napkin, and there are important things you can learn about sketching, and with a module on sketching we'll learn how important having proportion is. So we'll talk about that a little bit more in detail. And board drafting is a visual way of communicating a design or an idea. And we'll be talking about all of those a little bit more in our coming lessons. I hope that you learned something today, and thanks for listening.